Okay, so the last part of our class, let me just review a little bit of precise definition of limit. Okay. So this is the last part on the precise definition of limit that we learned. Okay, so the idea behind the precise definition, okay, is actually, if we are using the limit, this intuition or intuitive definition, that is, if we're getting close or we are approaching the functions from x to approach some value that maybe a, we will have, or we will get a value that closer to the L. Okay? And long story short, we simplify this and we can like ignore the small parts on the numbers like 0.9999, and we can say that in limit that is 1. We can say that. But the problem is we are not sure how short it is or how small the number is. So basically the precise definition comes up with some solutions to know whether is it close enough and how close for that number to be approaching the value that we are going to have in this L. Okay? So that's why we have another term to describe those numbers as the epsilon and delta. Okay? So every delta that should be the closeness of x to a, that is the delta. Okay. Epsilon is the closeness of the functions to the value that we are approximating. Okay. We are approximating. Okay. So we can write down in this equation here, okay, or the interval. Okay. So we write this as a small distance. So this is represent small distance or how close the x to a. Okay, so small distance. Okay. Yeah, this too. Okay, this is also small distance. Okay, we get epsilon and delta. Basically, when we are proving whether the limit is true or not, or how we prove, for example, the limit that is as x approaching 3 of 4x minus 5. Of course, if we are just use direct substitution, of course we are proving that this should be true. But we can also prove that using the delta and epsilon definition. So we can have some correlations between the delta and epsilon. So basically what we are doing is we move from this side, from the epsilon, okay? We take sometimes to simplify and look at the pattern and how it correlates with the first or the x, okay? The distance from the x. Okay? And we know that it will be 4 times the distance. Right? We have the 4 times here. Okay? So we want delta such that when you use that delta, it will be 4 times x minus 3 less than epsilon. So we see that, of course, this is 4 times. So we assume or we choose the delta to be epsilon number 4. So that when we use this epsilon number 4, it will go back to the original equations. So that's why we have proven by looking at this equation, we have proven that it is going back to our original equation here. That is using epsilon over 4 as our delta. So it's like you move from the end, going back to the original, and moving back to prove that, of course, our delta, that is epsilon over 4, is correct, and then it's proven that the limit is true, that it is equal to 7. Okay. Okay. So yeah, you can. This is just to emphasize what you're doing. Or actually, you can also write by delta equal epsilon over 4, it is true that this limit is equal 7, that's also fine. You can write with any words, but what you need to do basically you are looking on what is the delta, and then use that delta to prove that that is true. Okay. Of course, the more complex the limit is, that will determine how we are going to correlate the epsilon and delta. Okay. So, for example, I think the most or oftenly the complicated one is just the quadratic is already complicated. If you look at the limit, let's say we have limit. Okay, proof. Okay, this is proof. So if it is proof, so what we are going to do, we are going to have that epsilon delta definition. So first, maybe you can write that epsilon is a positive number. Then delta also positive number, such that we can start from writing all the information first that's supposed to be in the equation. So first is the distance of x, which is having a small distance delta, and then the functions x squared minus 9, which is smaller than the epsilon. Now we are going to find what is the relations between this epsilon and delta. Okay. First, to make our equations easily connected to x minus 3, I think the best way to look at is to separate the factors, right? So that we can have x minus 3 in here, right? We can have some connections. So we can write down x squared minus 9 as or factorize the x squared minus 9. So we can write if then okay, we can write that first. Okay. Now, to connect this to here, we have some problem with the x plus 3. Right? What we are going to do here. So, what we can do is we can assume that there is a constant. Okay, we have a constant. So, if we can find a positive constant, let's say positive constant c, so that the x plus 3, the distance x plus 3 is less than that positive constant c. Of course, this x plus 3, x minus 3 will also less than c, x minus 3. Okay. And we can take this, the c x minus 3, these terms, by taking that it should be less than epsilon. And then we can correlate the x minus 3 to be less than epsilon over c. So we want to simplify the x plus 3 into some constant that we assume. Okay. So from here we can look at that the delta seems to be epsilon over c. Okay. Now we need to define the c or elaborate more. Okay. That this is we restrict x to be in the interval centered at 3. Okay. So if we have the x minus 3 less than 1, this is again, this one is just to simplify or to assume, okay, that the distance is really small. Okay, you can try different number like half, maybe 0.1 if you want, but I think just 1 is, I think, easier to look at and to be used in the calculations. Okay, so if we have this, okay, or let me just write, it can be any small number. Okay, so if this is 1, then x will be from 2 to 4, right? And then the same way, if we plus the x, okay, let me write here. If we plus 3, then this will result in 7 and 5, okay? And now from here, with a small distance 1, we get the x plus 3. That is, at least this will result less than 7. So it seems if we use this number 1 here as just to imagine that it's small enough, okay, it seems that we can use this number 7 to be used in our C. Okay. But then we have two at least equations. That is, first is this that we assume here, right? And then if we are going to use the number 7 as in epsilon over c, then we will have this is less delta, or this is epsilon over c, or we can use 7. So choose c equals 7. Okay. Okay. So to make sure that these two, because it seems that we have two different inequalities, right? So we need to make sure that we have equation that covers both equations. So we take the delta to be smaller of number 1 and epsilon over 7. And usually we write these terms in a way that we write delta, mean, 1 epsilon over 7. Meaning, we take the delta to be smaller than 1 and smaller than epsilon over 7. Okay. It seems need another page. So, or maybe I will, because I think I can make the first part maybe going here. Maybe resize a little bit, put here. So here it is going here. Okay. Now, we are going to use this delta that is smaller than 1 and smaller than epsilon over 7 and check with the original equation. So we are going to use this. Okay. So checking delta. So we have 0 less than x minus 3 less than delta. Or let me write if, okay, then x minus 3 less than 1. So it will turns out to be this value. And this turns out to be x plus 3 less than 7, right? We also have x minus 3 less than epsilon over 7. So this is first one. This is the second one. So we can take the x squared minus 9. We are going to use the functions now. And then we exchange this x plus 3, x minus 3 with epsilon over 7 and 7. Okay. It turns out that it reverts back to just epsilon. Okay. So our assumptions or our delta can be used for the calculation, which is proven to be true. Okay. And by the conclusions, this will result proven to be true. Okay. Well, I must admit that the middle part here seems that it seems like it's really confusing, right? It seems confusing. Okay. Okay. So we move to the quadratic. It's already this complicated. Okay. So if we take more complex one, it's probably going to be crazy. But at least the last part before this, that's the line equations, the just standard line equations. It's I think by intuitions you know how to put forward and backward. Okay. This one you need to have good imaginations to get into how to make this in a logical definitions in terms of mathematics. Okay, so the key is actually this one. Okay? You need to have some constant that you can substitute, and then you can check the constant here, and you can use any small numbers. Okay. You can use 1, maybe 0.1, 0.5, but I think if you use decimals, it will be difficult to calculate that later on when you prove the equations. I think it's better just to use 1 to note that this is a small number. That is, what we are going to see is some distance that is smaller than 1. It's enough to prove. Okay. And later, we look on this equation. We have this 2 less than x less than 4, the interval, and then we can also approach x plus 3, and then we look on the number, it has a 7. So probably 7 is our best choice to check. Okay? And then we check 7 because it can help us going back to the x minus 3 later on, right? So we choose 7, and then we need to solve this less than 1 and less than epsilon over 7. We check the delta. We substitute the x plus 3 and x minus 3, and then we are going back to our x squared minus 9 by multiply both of this, which are, we are define these two by 7 and epsilon 7. And it turns out it's going to be the epsilon as the beginning mentioned. So this limit proven to be true. Okay. Okay, at least I think for precise definition of limit, there are some sections after this on precise definition, but I think I don't think it will be it will be really useful for you. So I think this one is useful to understand just what's the meaning of the limit itself. So I think I will just done here for the precise definition. Okay. Yeah.
In the quiz or the midterm, is there going to be a question about proving that the limit is true, or this is just to explain precise definition?
Probably proving part. But usually for the proving part, the equation should be obvious enough. To be obvious enough. Okay, I think we can move on to the next section. So the next section is about the continuity. And I hope we can finish continuity and maybe having some example. And if we near the end of the chapter 2, I think maybe next week, maybe next 2 weeks, maybe we will have maybe quiz. Okay. The schedule actually next week, Friday, but maybe next Tuesday. So next 2 weeks, I think that will be okay. And I think also. I need to maybe adding more practice. Maybe I will add maybe 2 questions in a video, and then you can watch. Okay, you can watch and learn.
Also, can you put your proving on the video too?
Okay. Okay, so continuity. Okay, I think for some parts in the limit at the beginning, I mentioned that we may have a curve that is not defined on some point on the curve, right? Generally, we can call this a discontinuity, or discontinuous also okay, or discontinuity, or we have the asymptote like here, like this one. We may also have. At least this is showing that there are no connection between the curve. Okay. Okay. If you want to visualize, like in your own words, what is continuous mean, when you write with your pencil or your pen, when you take your pen and you write again, that's discontinuous. That's discontinuous, the easy way to interpret. So whenever you find like this, like a hole or like an asymptote like this, you can directly call that, oh, that is discontinuous. And to prove that is what we are going to discuss, okay? So function, let's say function f is continuous, okay, at some number, let's say the number a, if the limit is equal, right? Okay. Previously in limit, we take the limit, and then we don't care if it has this discontinue. As long as we can approach from the left, from the right, the same value, we can say, oh, there is limit. But then there is no definition here. It's undefined, right? In the function itself. You can say, oh, it's discontinuity. So the continuity or functions has a continuous means that the limit is the same as when the function is plugged in by that number. So at least we have three implications. Okay, three implications. Okay. Okay. The function of a should be defined. So it's defined. Limit x approach a of f of x. This limit exists. So by the end of the day, the limit can be equal with the functions at a. Three implications, or maybe you can also say three requirements. Let me draw something on the right side so we can have some visuals. Okay, imagine that we are moving, approaching, like we discussed in limit, and this is approaching also the f. I think continuous or discontinuous, probably you will learn more advanced in if you maybe having some simulations, okay, or something related to electronics, okay, that will have some continue or discontinue. because like electric currents, it will have the discontinuity. Okay, but this definition we can break down one more time, because we can say that it's continue everywhere, right? From the left, from the right, we can approach, and then it's still continue. So we can actually separate, like one side limit. We can separate. Okay, so we can say maybe continue from the left, or maybe discontinue from the right. Okay, so we can also break down these definitions into function f is continuous from the right at a number a if limit as x approaching a from the right is also the same. Okay. And same thing, continues from the left at a if and you may know like some terms, removable discontinuity, jump discontinuity, but that term's not useful for you, I think. As long as you can define in the visuals and you know that it's discontinued, you can state that is discontinued, that's okay. Okay, let me give you an idea for to use this continuity. By the way, yesterday was your TA, right? How about the TA? Okay, he gave some, maybe how many questions he gave? How many problems? 7? 7? 6, 7? Okay. Okay, good. Okay, so show the function show the functions, that's the function 1 minus square root of 1 minus x squared is continuous on -1 to 1. Okay, first, if you just to show that this continue, you can take any a in at any points on the interval -1 to 1. So you can just mention A. So you can write A is, or maybe A is in between -1 to 1. And then we can just using the variable A as our limit approach. So our limit will be approaching x from x to some number A in between -1 to 1. So we can say that this is we can see that there's nothing wrong in here, so we can use that just direct substitutions because there's nothing anomaly, right? I think there's nothing abnormal here, so we can just direct substitute. It turns out that this is going to be our f of A, right? It's going to turn into our f of A, which means that it's just, if we plug in A, it's going to be 1 minus square root of 1 minus A squared, which is the same. Our limit is the same as its function value, which means by definitions, so by definition, f is continue at A if A is in between -1 to 1. We can also try to using limit. Okay. If you prefer using the numbers, maybe you can use number -1 and 1, and using this one side limit. This is equal 1, and this is equal f -1. And if you use the positive one from the left, you can also, it's equal of f of 1. So this means that f is continuous from the right. This is f continuous from
approach -1 from the right and 1 from the left.
Hmm?
Why do we approach -1 from the right and we approach +1?
This is actually up until this one, it's already finished. But you can also look at the I draw the functions. Okay, so I'll draw the functions here. The function is actually, if you look at the function here, okay, let me just write the functions. Okay, if I squared this, it will be a circle equations, right? If you it will be a semicircle, and then you can solve this if you want. But if you look at the equations, it's actually, if I draw this full circle like this, okay, maybe this, okay, so, and this is actually, okay, actually this is what this looks like. So this will be -1, and this will be 1. So we approach -1 from the right, and we approach 1 from the left. Okay. I think it's better if we can visualize like in any graph, right? And I also prefer if I maybe confused on the equation. Sometimes if it's easy to be graph, I would choose picture because I think it helps. Also, when you study, I think it's also can be really helpful because I think mostly people prefer visuals because they can believe what they understand in a picture, and it seems that it's faster to be understand rather than reading the words, right? And sometimes we prefer watching movies rather than read the book, like watching videos may be better than read the book. But I think different people also different approach, and it's up to you which one you are going to prefer. Okay, there are some property that need to be looked up. Okay, so properties of continuous function. Okay, if f and g both continue, let's say at A, and or maybe just so that we can avoid confusion, let C be a constant, then all the followings will be continuous. So f plus g, f minus g, f multiplied by g, f over g, but g should not be 0, or g of a to be precise. G of a, and then constant multiplied by a functions is also continuous. So all of this are continuous, also continuous function. So we need to make sure that both f and g, each one of them need to be continuous, so that we can apply all these terms. And from here, we can get some general theorem for some functions that mostly appear in our calculus, okay? In the calculus. Okay. So let me just go through. Okay. So another theorem. Okay. Any polynomial or any polynomials or any polynomial is continuous everywhere. So it is continuous on all real numbers, which is from negative infinity to positive infinity. Okay, because polynomial is general functions. And any rational function is continuous wherever it is defined. This is to note the denominator that may be not continuous, or that is it is continuous on its domain. So the key, I think, for most cases is the rational functions, especially the denominator that you need to be taken care of. Okay, if we have limit as x approaching -2, let me just write this first, and 5 minus 3x. This will be, it seems that this is rational functions, right? And in the denominator, you will see that we should not have the denominator to be 0, right? So we need to have some exception. So we have some certain domain. Do you want to take a break, or do you want to maybe later, maybe faster to be finished? Continue. Okay. Yeah, because I think that it's like the end of the day, right? Okay, so by looking at the functions, if we take the functions as, so if okay, any questions? Any questions so far? Okay. Okay, so if we have this function here, okay, this is rational, right? Rational functions. Rational functions. So we can take the definitions of rational functions, that is, it should be continuous on its domain. So what is the domain for this rational? Of course, this is just to ignore this part, right? This is the denominator. So we need to have some exception so that the domain will be x, all x, except at x equals 5/3. So we can make exceptions on one point, right? On the point of 5/3. So therefore, when we are using this definition of continuous, we can say that if we are going to limit this, that this is going to be that is precisely just direct substitutions to the functions. Okay. Basically, if you just focus on how to get the limit value, you can just direct substitute. What I want to show here is to get the idea on why this is equal this, we can go by definition of a rational function. That is what is continuity on rational function, which is continuous its domain. Okay. So because x is not 5/3, so we don't need to be worried about this -2, right? Maybe after some parts in chapter 2, because I haven't yet really practicing some questions. Maybe after we get to maybe 2.6 or 2.7, I will go some review and maybe we have some practice. And maybe after 2 class, 3 class, we will have some kind of feedbacks like last time to know whether you get the idea or not. Okay, another theorem that is probably will be considered if functions continues at b and limit as x approaching a of gx is b, okay, then limit as x approaching a f and then gx is like a composite function. This is equal f of b. In other words, we can take this so whenever all already defined, continuous, and we have some like finite value b to determine this limit, we can take the limit, the closed limit inside the function. Okay. This is to connect the idea of composite functions, the FFOG, right? Okay, and then still the composite, we can also write down some definition of continuous on composite. If G is continuous at A, okay, and F, both are functions, okay, is continuous at G of A. So G, A, F, G, A. Okay, so then FOG or F G of X is continuous at A. we get, because this is a composite, which means that a function inside the functions, right? Functions inside function. Functions G inside F. So what we are saying is, if this is the inside function continues at A, then the whole thing also continues at A. And if this F is continuous at this, then the whole thing will be continuous at A. Or a continuous function of a continuous function is a continuous function. Okay, so you are looking from the inside, going outside is continuous. The conclusion will be continuous function. Okay. Okay. And last part on continuity, we call the intermediate value theorem. Intermediate value theorem. Okay, suppose that function f is continuous on closed interval from A to B. Okay. And let n be any number between f of A and f of B, where f of A is not equal f of B. F and then okay, there exists, which means it can be more than one number, a number C in AB such that FC is equal n. Okay, this is saying that when you have a graph, let's say we have this. Okay. Let's say this is our f of x. And we evaluate the graph from some interval A to some B, maybe here. Okay. And of course, f of A is not equal f of B. So f of A. This is f of B. So there will be some number, maybe n here. That is, if you look at this graph, it will have some C on x-axis, like that. Okay. And of course, the C, it can be more than one. Like for example, if you have another n, okay, because n can be in any value, you can have maybe n here. So it can have C1, C2, and C3. This is just to illustrate that C can be more than 1. But all that C will be n for its value. If we check one by one, it's n, still n. This theorem, it seems that, okay, if we have bucket here, we have the interval, and of course, if we have the value between the value of f of a and f of b, of course, the results, if we find the x, the f or the c, it will be between a and b, right? It will be more obvious, okay, if you imagine f of a and f of b they are divided by the y equals 0. So if we imagine maybe here, if we imagine that this is x, y, and then imagine that maybe f of b is here and f of a is here. If we imagine this, for sure that the graph will be crossing the x-axis, right? Okay. For sure, it can be this, or it can be this, right? But either way, both curves should cross the x-axis. So at least the intermediate value theorem can predict if you have some curve, like either polynomials, quadratic, or whatever, you can know the root of that curve because they will certainly crossing the x-axis if f of b is here, or f of a here, or f of a or f of b here. Okay. Okay. So if I give you like maybe some really complex, maybe x with power of 5. If you just plug in some numbers that are easy to be calculated, and you know that there will be a negative and there will be a positive, you will know for sure that those curves will crossing the x-axis. And if you just proving that this is maybe negative and positive, you're already proving that by using intermediate value theorem, there is at least one root. Okay. The curve may be like a crazy curve, like, but if you can get one is positive, one is negative, for sure there will be something in the middle, right? Okay. Let me give you some illustrations. 4x cubed. Okay. Maybe the question is just show that there is a solution for the equation given. So of course, if it's asking the solution, it's asking exactly what I mentioned before. It's asking the root of from this equation, okay? Which means we need to take some numbers that has different value or opposite signs. So first, we can design these equations to be our function. So basically, there is a number C such that FC is 0. So basically, this is what they mean by solution. This means by root or solution, right? And then how we are make sure that this is true, we need to take some samples. The samples can be taken from any numbers you can think. If we take 1, let's say 1, this will be 4 minus 6 plus 3 negative 2. This is negative 1, right? If you take 0, I think it's still negative, right? It's still negative 2. Maybe number 2. Assume number 2 will be a positive because 2 having positive on the cubic, and then having another one here. And I think you can figure out just by looking at the equations. If the biggest one, the biggest power having maybe negative, then maybe you can check with the negative x, like negative 1, negative 2. That is easy to compute, and make sure that you have some value that is positive or negative. And we get the, let me check, okay. So this is positive, right? So since this is negative, or maybe let me write with the red color. Since this is negative and this is positive, for sure that there will be something in between. So we don't really need to draw the curve to prove, okay? At least we know that from our computation, from our evaluations, when you have, let's say this is 0, maybe 1, and maybe 2 here. So when you have 1, you have this is negative 1, and we have 2, this is here. This is 12. So it will be going down like that. Okay. And the curve, we don't really care what the curve will be, okay? Because that is not our case in the given questions. So we know that if we want to write, like completely write the answer, we can write something like this. But for our case, or for my case, it doesn't really important to write completely, as long as you can give visuals, you can give some proof on why this having the opposite sign. I think that's still enough. So f of x has at least one solution on interval 1 to 2. Okay. Okay, probably this will be last 10-15 minutes. This will be the next sections, the horizontal asymptotes. Okay, horizontal asymptotes. So this is called the limits at infinity, or we call that implications as horizontal asymptotes. Okay. Let me go to some website first to get maybe some graph. Squared minus 1 x squared plus 1. Okay, let me take the screenshot and moving on to our subject here. Okay. Let's say this is functions. Let me write the functions here. Okay. When you look on these functions, when you zoom out, and zoom out, you see that when you approach x to some numbers to the left and to the right, it will have certain value, right? In this, around this number 1 here, right? So we can write down here or create some line on this y equal 1. Okay, so as x becomes large, f of x get closer to 1, but it doesn't seem to be touching 1, right? It has some like small distance. If you look on the left and then you look on the right, it seems that there's small distance, like almost closer and closer. And again, this is what we call asymptote. So if you remember, previously there is a vertical asymptote. It actually works the same. All asymptote works the same. The curve will not touch those asymptotes. Okay. So we can express this this curve or this phenomenon as any limit as x approaching infinite. Of course, we can have a positive, negative, infinity. Okay, but let me just write in general first. So in general, we can write limit as x approaching infinity of f of x equals some L. So to indicate values of the functions approach some L as x becomes larger. larger and larger to denote that it's getting bigger, really big. Or we can make more mathematics. Okay, if we set up some restraint, so we can have some definition that f be a function defined on some interval. Okay. Okay. And then means that f of x can be made closer to L by requiring x to be sufficiently large. Well, basically, it's the same way to say, but it's more rigorous or more official. But for me, okay, that doesn't mean that if you writing an exam, you need to be right as in the textbook mentioned or as in the official words. That's not important. For me, the important thing is you understand how the graphs work, how the definition works. Okay. You can use any simple words to define those words. Okay. No need to be really perfectly similar, same as my words here. No need. As long as you know what's the meaning of this limit, okay? And you can describe this in visuals. You can describe in maybe in numbers. That's enough. That's all mathematics want you to care. You do not care about and also the formula. We don't really care about the formula actually. Sometimes we tend to be memorizing formula because that is the way we are learned. But that's not how we are. That's not how it's going to be work in our case in this university level. As long as you understand, how it came, all the formula can be really derived from one formula to another. So like if like simply you maybe forget and like trace back what is the connection between this and this and this. Okay? Okay, so just some small example on the graphs, and then we finish our topic. Okay, maybe this looks like this, and then it's having some asymptote, and then another one maybe around here, going there, and then it's going to have asymptote again here, and then maybe this, and then maybe this will be asymptote here. Okay, so there are several examples on how the visuals will looks like. For example, maybe the left part is going to be like fluctuations. It goes up and down, but eventually when this goes right, it goes to some value, and we can say also this is having the asymptote here, right? As the x approaching infinity to the right, it will goes asymptote. Also here it's decreased, but it stopped here and then goes to some fixed constant value here, and it's the asymptote. And if you have some fluctuation, like maybe in having some trigonometric, But those fluctuations, maybe I'm not really drawing really well. Maybe it start like big like this, but it's become smaller, and then it's getting closer to a small or smaller curve. That is, you can trace down with some line. That's also the horizontal asymptote. Okay. We can read the curves as limit as x approaching infinity. That's okay. Or as x maybe getting unbound is also fine. Anyway, it's fine. Like maybe larger and larger is also fine for me. Okay. No need to worry about how you write the words. Okay? If you feel maybe you need to write really precise, no need to be worried. Okay, I think that will be the end for our class today. Okay, hopefully, maybe next week we have some, after we finish maybe 2.6 or maybe 2.7, we can have some review and some practice. Okay, any questions so far? No? Okay. I hope it can be enjoyable, okay, this semester.